Okay. So, now this capacitor actually initially assume it was charged say some voltage say V0, not necessarily that it will be charged all the time, V0 can be 0 also, but we assume that this capacitor initially was charged at V0 just to get a generalized expression, right. So, what you can do this, right. So, let us assume an initial voltage V0 on the capacitor, but this is not necessary for the step response, right. Since the voltage of a capacitor cannot change instantaneously, that is V0 minus is equal to V0. What I want to mean for this circuit, right, for this circuit, that when switch was not closed, it was open initially, suppose this capacitor was charged as voltage V0, right. Suppose this voltage, if I write say it is say your V0, just I am making it say V0 minus. So, as soon as the switch is closed, that your what you call the capacitor voltage cannot change instantaneously, that means it will be actually V0 plus just before switching and just after switching, it cannot change instantaneously. Earlier also we have discussed this. So, V0 minus will be V0 plus, this just before switching and just after switching, right. So, let me clear this, because sorry, just hold on. So, now let us come to the circuit. So, it is given V0 minus is equal to V0 plus, this way I have written is equal to V0, just your before switching and after switching, that capacitor voltage cannot change instantaneously. So, this is equation 44, where V0 minus voltage across capacitor just before switching and V0 plus voltage across capacitor just after switching, right. Now, applying KVL, I told you it is V minus your what you call Vs ut upon R plus C dV by dt. This already I have told you, and for t greater than 0, this ut is 1. So, it will be basically V minus Vs upon R plus C dV by dt R is equal to 0. Actually, it was circuit was like this, no? I am drawing it here. This is your Vs, your ut, right. This is Vs ut. This was your R, right, and this side it was your capacitor, and plus minus this voltage was V, right. So, some point if current direction was taken like this IT was taken like this, right, IT was taken like this, and IT is equal to, we wrote no, IT is equal to, that is your IR plus V minus V, that is your Vs ut minus V divided by R, minus this V divided by R. This is in this direction clockwise. Now, if you take at any point here, say this point is A. Now, if I take one current is going like this, just you think like this, and one current IC is going like this, although IC is equal to minus thing. So, this point if you apply your what you call that your KCL, then this as direction is changed, so it will be V minus Vs ut. So, V minus Vs ut R divided by R plus your C, this capacitor C into dV by dt is equal to 0, right. Now, for when this as soon as the switch is closed for t greater than 0, that ut is equal to 1. That is why this ut you put here, it is written, but after that this Vs ut it is written like this, right, but ut is equal to your 1, we will come to that. So, this is actually this one, if you simplify, it is dV by dt plus V upon RC is equal to Vs upon RC ut. Now, for t greater than 0, then we had the time ut is equal to 1. For units function we have seen, for t less than 0 ut is 0, for t greater than 0 ut is equal to 1. So, that is why in the derivation now ut is not there, because it is we are trying to obtain the response for t greater than 0, little bit understanding is required. For t greater than 0, our objective is to find out the response for t greater than 0. So, this equation 45 becomes, so ut is 1. So, it is dV by dt plus V upon RC is equal to Vs upon RC, or dV by dt is upon simplification V your what you call minus V minus Vs upon RC, or dV upon V minus Vs is equal to minus dt upon RC. This is equation 46. Now, you integrate both sides. So, initially capacitor voltage across the capacitor was V0, and at time t it is Vt. So, you are making V0 to Vt, dv upon v minus vs is equal to minus 1 upon rc, that integration 0 to t dt, right. So, if you integrate this, it will be natural log ln v minus vc, limit, your integration limit is v0 to vt is equal to minus t upon rc, here also 0 to t. So, this is equal to ln v minus vs upon v0 minus vs is equal to minus t upon rc. That means v0 minus, so it is natural log means log of base e, right. So, it is v minus vs upon v0 minus vs is equal to e to the power minus t upon tau. Tau is equal to RC, the time constant of RC circuit. This is RC, this is equation 47, right. So, or Vt, upon simplification, just cross multiply and simplify, you will get Vt is equal to, actually what I am doing is this, up to this it is written your what you call, all the time not putting your what you call Vt, right, but now this V is replaced by V. It is understandable to you, it is a function of time, it is understandable to you. So, that is Vt is equal to Vs plus V0 minus Vs e to the power minus t up by tau. This is for t greater, every time you have to write when writing this for t greater than 0, right. Therefore, you can write, because Vt is equal to V0, initially capacitor was charged at voltage V0, that is for t less than 0, that means complete response of voltage you can write Vt is equal to V0 for t less than 0, right, and Vt is equal to this expression Vs plus V0 minus Vs e to the power minus t by tau, this is for t greater than 0. This is we call the complete response, much more we will see very soon, right. So, this is your what you call, this way you can write. So, for that this is called the complete response, that is in general minus infinity to your what you call that t greater than 0 means plus infinity, but you know that for earlier we have seen that up to 5 tau time constant, basically that the responses or I could say that dynamic the circuit responses, it reaches to the steady state, right, for t is equal to say 5 tau, because it becomes just your what you call, it is becoming your what you call less than 1% of the peak value, right. So, 49 gives the total response of the RC circuit to a certain application of DC voltage source, that is RC circuit we applied assuming the capacitor is initially charged, right. Now, if it is assuming that initially uncharged, that means V0 is equal to 0. So, if V0 is equal to 0 in this expression, if V0 is equal to 0, put it, in that case Vt will be equal to 0 for t less than 0, and here also if you put Vs is equal to your what you call V0 is equal to 0, it will be Vs into 1 minus in bracket 1 minus e to the power minus t by tau. So, here it is 0 for t less than 0, and it is Vs 1 minus e to the power minus t by tau for t greater than 0. This is equation 50, right. So, that means alternatingly this equation you can write this equation other way, that it is Vt is equal to Vs 1 minus e to the power minus t minus into ut, because ut written for ut you know for t less than 0 ut is equal to 1. So, if when ut is equal to 0 for t less than 0. So, when t less than 0 ut is equal to 0, then Vt will be 0. So, it is 0, and for t greater than 0 ut is 1. So, when ut is equal to 1, it will be Vs 1 minus e to the power minus t by tau. So, combining these two, we can write Vt is equal to Vs 1 minus e to the power minus t by tau into ut. This is equation 51. Hope this is understandable to you, right? Not very simple thing. So, his figure is this equation 51 is give the complete response of the RC circuit when the capacitor is initially uncharged, right. So, current through the capacitor is obtained from equation 50, that is nothing but IT is equal to C into dV by dt. So, you take the derivative of your what you call your for t greater than 0, you take the derivative of this equation, the dVt by dt for this one for t greater than 0. So, when you do so, IT is equal to C dV by dt, that is here you have to write t greater than 0, right, that is C by tau, then Vs e to the power minus t by tau, you take the derivative of this equation, right. So, it will be your basically, and your this is C by tau Vs e to the power minus t by tau, and tau is equal to RC, right. So, here tau is equal to say CR. So, if you put tau is equal to CR, so C by tau is equal to T by CR, C cancel, it will be 1 upon R, that is why Vs upon R e to the power minus T by tau, right. So, and in general if you want, then IT is equal to Vs upon R e to the power ut again, right. Here it is ut, same philosophy for t less than 0 ut is equal to 0, and for because circuit was open, so I was 0, and for t greater than 0 ut is equal to 1. So, that is why again it is ut is multiplied, right, because at that time t less than 0 the switch was open, right. So, now equation 48 is rewritten as, we have again this equation 40 is this one, Vt is equal to Vs plus V0 minus Vs e to the power minus t by tau. That means Vt is equal to, can be written as Vss plus Vt, that is your steady state response plus transient response. So, therefore, complete response, the Vt is the complete response, is equal to steady state response plus transient response Vss plus Vt, right. This is your what you call Vs is the steady state response, and this is transient response, because when t tends to infinity, if you look into that, when t tends to infinity the circuit reaches to steady state. If you come to the circuit, from the circuit only, because this we have to use again and again for solving your numericals, and we have to, if you come to this circuit, right. So, capacitor, when the switch is closed for long time for do DC, because the switch is closed for long time, the capacitor act as your what you call open circuit, right. So, this is not required at that time, no need to do that, because ut at that time ut is equal to 1 for t greater than 0, and if it is, and that means this is only Vs, this is not required. Suppose Vs and capacitor is open, then what is the voltage across this, what is the voltage across capacitor is open. So, basically V is equal to your what you call in that steady state voltage in V infinity, sometimes we call Vss steady state, right, is equal to actually Vs, this source voltage, right. So, this is from your intuition you can find out, because to DC when switch is closed for long time the capacitor act as open circuit. So, this is actually just I am making it like this, and V will be is equal to Vs, and at that time circuit representation is like this. So, ut is equal to 1, right. So, anyway, so again we will come back to this. So, this complete response is here also if t tends to infinity, here also if you make in this expression t tends to infinity, the second term will vanish, and it will be your I mean if you move like this, just hold on, if t tends to infinity, that means this term will vanish, that means at that time Vt will be V infinity, that is your steady state value, that is your Vss will become your Vs, this value, right. So, that is your steady state value, that means this is your steady state value Vs, and this part is a transient part, and this part is your steady state part. Let me clear it, right. So, that is why Vss is equal to Vs, and this is transient part, this is equation 55, this is equation 56. Right. So, transient response is a temporary, and it is the portion of the complete response that your what you call that decays to 0 as t tends to infinity, because when t tends to infinity, your I told you when t tends to infinity this part term will vanish, right. So, that means transient will vanish, only left out portion will be that is steady state. So, that therefore, and it is the portion of the complete response that decays to 0 at t tends to infinity. The steady state response is the portion of the complete response that remains after the transient response has died out, I mean when transient is over, right. Thus, the steady state response is the behavior of the circuit a long time after an excitation is applied. That means voltage source, suppose it is switched on, and your steady state will achieve after long time, right. So, the complete response of equation 48 may be written as, this can be written as something like this. If you come to this one, if you come to this response, this one, I mean this one, look, this one, this is the thing you are obtaining at infinity, and this is your initial value, and this is again you are at this Vs is actually your at t tends to infinity, your V infinity is equal to Vs, right, that is steady state value, and initial value V0 was is equal to I can make it V0, right. That means this equation Vt I can write like this Vs is equal to steady state value, that is V infinity plus I can make V0 minus V infinity, right. Then your this one e to the power minus t by tau. That means Vt will be V infinity plus V0 minus V infinity e to the power minus t by tau. That means if you know the initial values, if you know the final values, the steady state values, and if you know the time constant, easily you can compute Vt, right. This you have to keep it in your mind for solving numericals, and for the exam also you have to keep it in your mind, right. So that means this one we can write the Vt is equal to V infinity, this is the final value V infinity plus initial value, that is V0 minus final value V infinity into e to the power minus t by tau. This is equation 57, right. So V0 is the initial voltage at say t is equal to 0 plus just after switching, because capacitor to capacitor the voltage cannot change instantaneously. So V0 minus is equal to V0 plus, right, and V infinity final or steady state value, right. So this equation Vt can be written as V infinity plus V0 minus V infinity bracket close e to the power minus t by tau, right. Therefore your note that if the switch changes position at time t is equal to t0, so whatever we are considering that is at t is equal to 0. Now suppose if the switch changes position at time t is equal to t0, t0 is say not is equal to 0 for example. So instead of t is equal to 0, there is a time delay in the response of that equation 57, right. So there will be a time. In this case what will happen? Before going to this thing, in this case this will remain as say V infinity plus, now this was there when t is equal to 0. Now switch is on at t is equal to t0, therefore initial values will be V, it is Vt0 minus V infinity will be there as it is there as, then e to the power minus then t minus t0 divided by tau. So this was actually at t is equal to 0, switch was just close at t is equal to 0 plus say, right. So but now if we make it t is equal to t0, then it will be instead of V0 it will be Vt0, right, but V in steady state will remain same V infinity plus your Vt0 minus V infinity, then e to the power minus instead of t it will be t minus t0 divided by tau, right. So let me clear it. So this is the expression Vt is equal to V infinity, what I told, plus Vt0 minus V infinity, then e to the power minus t minus t0 by tau. This is equation 58. Now where Vt0 is initial voltage at t is equal to t0 plus. If t0 is equal to 0, then it will be V0, right. Here also it will be e to the power minus t by tau if t0 is equal to 0. So this is that your what you call the RC circuit, that your what you call that your initially you have studied the source free, now you are studying that your circuit is involved with sources, right. So now look the example. So in figure this is 41, the switch has been in a position A for long time. That means if you look into the circuit, that this was in this position for long time at position A, this is A, right. Now at time t is equal to 0, the switch changes its position to B. Now at t is equal to 0, the switch is you are changing in position from A to B, right. Obtain Vt for t greater than 0 and obtain its value at t is equal to 0.5 second and t is equal to 3 second. Now this switch was at its position for long time at A, right. That means circuit at that time, for that case circuit was a steady state because switch was at this position and for long time, that means this capacitor is open circuited and the voltage your this voltage Vt actually you have to find out across this thing, this is the voltage V across the capacitor and capacitor value is 10 to the power minus 3 farad. So at that time this was open, right, but that means you have to find out the initial values of the your what you call voltage across the capacitor initial, because switch is moved now after that at t is equal to 0, switch will move from A to B. So in that case what will happen, that first as this is open circuited, that means this voltage this voltage was V, right, and say this is V and this is V0, right. So, in that case it is open. So, first you find out what is the current here. So, current through this is I, and I equal to your 48, right, divided by 6000 plus your 10,000. 10,000, this is your writing on it all ampere, right. And then what is the voltage across the capacitor, because capacitor is open circuit, this is open circuit. Therefore, your V is equal to your this is the current 48, 6000 plus 10,000, this is 16,000 into this is this point, you find out the voltage across capacitor into your 10,000, this much of volt. So, this is your V, right, because switch was at this position. So, capacitor was open circuited for a long time. So, now let me clear it. So, whatever we have made it, that whatever this is whatever I told, that 10,000 by 6,000 plus 10,000 48, it will be 30 volt, right. That means just before switching V0 minus, the voltage, that initial voltage across the capacitor was 30 volt. Now, switch is closed, right. Therefore, say your that means you are using the fact that the capacitor voltage cannot change instantaneously. So, which switch is closed, V0 is equal to V0 minus is equal to V0 plus is equal to 30 volt, right. So, now switch has moved from this position to that position, right. So, now switch has moved there, this part is not there, switch has moved from this position, though this part is not there. So, capacitor is your 10 to the power minus 3 farad and 8000 ohm. So, first you have to find out the time constant of the circuit, it will be then 10 to the power minus 3 into your 8000, right. So, it is CR. So, it will become your 8 second, right, this will be tau, because switch has moved from this to that. So, just let me clear it. So, in this case tau is equal to, I told you, 8 second. Now, since the capacitor acts like an open circuit to DC, at the steady state V infinity is equal to 60 volt. Now, come to this circuit. Now, when switch position is your what you call switch position is like this side is not there. So, switch is closed at B, moved from B, and for a long time, that means a capacitor will act as your what you call an open circuit. At that time, what is the value? That is the V infinity, right. So, as it is open circuit, so V infinity, the final value will be just 60 volt, because this 60 volt is applied across this, and switch was closed at this position for a long time, that means this is open, right. So, V infinity will be 60 volt, and initial voltage V0 your 30 volt we got, right, and tau we got, it is 8 second, right. So, we will apply that formula. So, let me clear it. So, here it is from here it is V infinity 60 volt we explained. Now, Vt is equal to, you know this formula, Vt is equal to V infinity, Vt is equal to V infinity plus V0 minus V infinity to the power minus T by tau. So, V infinity is 60 volt, V0 we calculated 30 volt, 60 volt e to the power minus T by 8. So, it is 60 minus 30 into e to the power minus T by 8 volt, right. Now, at t is equal to 0.5 second, you put here at t is equal to 0.5 second. So, V at t is equal to 0.5 is equal to 60 minus 30 into e to the power minus 0.5 by 8. So, it will become 31.817 volt, right. And another one is that at t is equal to 3 second. So, at t is equal to 3 second, you put here t is equal to 360 minus 30 into e to the power minus 3 by 8. So, that is 39.38 volt. These are the answers, right. So, hope you have understood. I hope you are understanding this. Just little bit, you know, so many varieties of problems you are solving. Just open any good book and just take few problems and just try yourself, because whatever variations of problems are there, perhaps trying to cover all types of your problems, such that whatever book you will open, you will find problems are almost similar to that whatever has been done here, right. So, next one is that in figure 42, this is figure 42, you have to actually here, no, understanding is more required. just blindly we cannot do this. We have to understand the philosophy or physics behind this switching circuit, right. So, in figure 42, switch S1 has been closed for a long time. This is your switch. This switch actually, this switch S1 was closed for a long time, right. And then your at t is equal to 0, that the switch S2 is closed. The another switch is here S2, that at t is equal to 0, switch S2 is closed. You have to find out Vc0 plus, Ic0 plus, that your Vc0 plus means this one that is that your voltage across the capacitor Vc0 plus. So, Vc0 plus is nothing but the Vc0 minus, because at the time of switching that voltage cannot change instantaneously across the capacitor, right. And you have to find out Vc infinity, that means this one, what will be the final value of this one, and Ic infinity, what is this Ic infinity, what is the steady state value. Also derive expression for Vct, that is the voltage across the capacitor. All these things we have to do it, right. And this is 20 ohm, and this switch was closed for long time. So, let me clear it. So, this switch S1 was closed for long time. Now, look, the switch was closed for long time, hence before S2 is closed the capacitor is fully charged. That means, if capacitor is fully charged and this was is open, that means, just let me make your thing clear, that means this was open and the switch was closed for long time, that means capacitor is acting as your open circuit. That means this is your say Vc 0, your what you call that Vc 0 minus, right. So, as this is open, this is also open. So, no current flowing through this. So, basically your Vc 0 minus will be equal to 10 volt, because this is the voltage across the capacitor. So, let me clear it. So, this is your Vc 0 plus is equal to Vc 0 minus is equal to 10 volt. Now figure, this next figure is that switch S2 is closed, right. Now, switch S2 is closed, S1 was closed, now at t is equal to 0, switch S2 is closed. Now, this switch is also closed. So, at the time of just at the time of t 0 plus, you apply KVL and KCL, right. So, if you at the time of when switch is closed, just at the time of your this switch, at the time of your what we call just switch is closed, right. At that time you apply KCL and KVL. So, here if you apply your KVL at your in this mesh, right. So, how it will look like? It will be 20 I1 0 plus Vc your 0 plus minus 10 is equal to 0. Just let me this thing. So, here we are writing 20 I1 0 plus Vc 0 plus minus 10 is equal to 0. That means 20 I1 0 plus Vc 0 plus is equal to your what you call 10. I mean, as soon as the switch is closed, little bit understanding is required. You apply here this your what you call that your KVL. So, it will be 20 I1 0 plus, that is just at the time of switching, just after switching, plus this voltage at that time across the capacitor is Vc 0 plus minus 10 equal to 0, right. So, we know Vc 0 plus. So, let me clear it. So, in this case Vc 0 plus is equal to your this thing 10 volt. So, I1 0 plus is equal to 0 ampere, right. Here your Vc 0 plus is equal to Vc 0 minus is equal to 10 volt, because through capacitor at the time of switching again and again I am telling voltage cannot your what you call across the capacitor voltage cannot change instantaneously. So, in that case I1 0 plus is equal to 0 ampere. Now, come to I2 0 plus. Now, I2 0 plus your this is your I2 0 plus, and at that time voltage across the capacitor, that is Vc 0 plus. So, it is 20 ohm is connected across this. So, I2 0 plus will be Vc 0 plus by 20. So, Ic 0 plus is equal to your Vc 0 plus by 20. So, Vc 0 plus is 10 volt. So, 10 by 20 0.5 ampere, right. Also, if you apply here at this point, if you apply at this point your KCL you apply at this node, right, then you will get your I1 0 plus is equal to Ic 0 plus I2 0 plus, right. So, that means I am writing here I1 0 plus is equal to your Ic 0 plus, right, plus I2 0 plus, right. You apply KCL at this point. So, let me go to this. So, here I10 plus is equal to IC0 plus plus I20 plus. So, your what you call I10 plus was 0. So, IC0 plus I20 plus is 0.5 is equal to 0. So, IC0 plus is minus 0.5 ampere, and tau is equal to C into R Thevenin. So, it is 5 into 10 to the power minus 6, C value is given, and R Thevenin means this one, right, across the I mean you have to find out R Thevenin. So, this is the terminal for the capacitor, right. When you find the R Thevenin, this voltage source is shorted, we have seen this, right, and this 20 ohm and this 20 ohm both are in parallel, right. So, it will be 20, because at this point, say this is point A, this is point B, we are trying to find out R Thevenin. So, it will be 20 into 20 by 20 plus 20, this is your R Thevenin, you have to find out. Therefore, R Thevenin is equal to 10 ohm, right. So, because this we have seen before, that your what to call, how to find out your what to call R Thevenin, right. So, this so we got this one, your what you call this R Thevenin is equal to, directly we are writing 20 into 20 upon 20 plus 20. So, basically it is your what you call, that is 10 ohm. So, multiplied by 5 into 10 to the minus 6. So, it will be 5 into 10 to the power minus 5 second, right. And at t tends to infinity, capacitor acts as an open circuit. So, for this thing, switch is closed, and it remained closed for long time. So, capacitor will act as open circuit. So, IC infinity is equal to 0, because capacitor will remain open circuit when switch is closed for long time. Therefore, right, IC infinity 0, and VC infinity will be 10 into 20 by 40 is equal to 5 volt. So, if you come here, what will be your VC infinity, right. So, if you look into that, the capacitor acts as open circuit, right. So, question is that this is open, this is open, right. So, this is open circuit. So, find out what is the current flowing through this, So, this is open circuit. So, what is the current flowing through this, the I, it is 10 by 20 ohm plus 20 ohm. So, 20 plus 20, so 40, that is 1 by 4 ampere. This is your what you call the current flowing, and this voltage this 1 by 4 ampere. So, at that time nothing is there, it is a steady state, it is at infinity. That means, and then open circuit voltage, I mean voltage across the capacitor, that VC infinity, right, that is VC infinity, this is your voltage VC infinity, this is the voltage, right, is equal to your this 20 into this 1 by 4 ampere, that is equal to 5 volt, right, because capacitor is open circuit at the time. So, current you have to flowing like this, and this capacitor is connected, this 20 ohm resistance is connected across the capacitor, right. So, you can find out easily VC infinity 20 into 1 by 4, so 5 volt, right. So, let me clear it. So, that means VC0, VC infinity all are known to us, right. So, that is your 5 volt, this is VC infinity, directly I have written here, I hope you have understood this, right. Therefore, VCT is equal to VC infinity, the same formula, that VC infinity plus VC0 minus VC infinity e to the power minus t by tau, generalized formula. You substitute VC infinity 5 volt, VC0 10, VC infinity 5, and e to the power minus t, then by 5 into 10 to the power minus 5, that is tau, time constant for t greater than 0. So, that means VCT is equal to 5 plus 5 e to the power minus 2 into 10 to the power 40, that is volt, that is for t greater than 0. Hope you have understood this, little bit understanding is required. Thank you very much, we will be back again.